Hello friends. Parallel processing is one of the most important topics in your COA course. In parallel processing, we make our system to work parallelly towards multiple programs or multiple executions. In parallel processing, the first important topic is called pipelining. In this lecture, we'll discuss about pipelining in detail and also we'll discuss about different types of hazards in pipelining such as memory hazards, data hazards, and instruction hazards. So without wasting your time, let's start the discussion. So the very first topic in parallel architecture we'll discuss is about pipelining. So in this lecture, we'll discuss what is pipelining and how to deal with this. Now, before we move on to the actual discussion, let me explain what is pipelining with the help of one example. For example, you suppose you opened one restaurant and you hired some employees for that. Suppose for customer management, you hired four employees. Now, what do you mean by customer management? Maybe to welcome the customer, to serve the menu to the customer, maybe to offer additional services, right? To get the feedback. So to provide those kind of services, you hired four employees. Now, say in day one customer came and all your four employees are busy serving the customer. Busy in the sense, someone will welcome, someone will serve the welcome drink, someone will ask for the additional services, someone will provide the menu cards and all. Fine. So it's happy. The customer is happy and you are serving your customer very well. Imagine that at the same time or after some time, one more customer came. Customer number 2. Now your manager will ask your customer 2 to wait on the table because all your employees are busy in serving customer number 1. Fine. So after some point of time, it's fine. Customer 2 can wait for a few minutes. Fine. Maybe after some point of time, one more new customer came. Customer number 3. And your manager is asking your customer 3 to be in the queue because your all employees are busy serving customer number 1. After that, they will serve customer number 2. Then they will come to customer number 3. So customer number 3 also somehow okay to wait. Now imagine about customer number 4, 5, 6, 7, 8, 9, 10. Do you really think they will wait that much of time just to get the welcome drink, to get the menu card, to get other basic facilities? They will be there in the queue. Do you think really they will be in the queue? In reality, no. No customer number 9, 10 will wait that much time to get the basic services, right? Now, what is the alternate option? The alternate option is what you can do. You have 4 employees, you can divide the task. You can divide some tasks to each one of the employees. For example, employee number 1 will welcome the customer. Employee number 2 will give the menu card to the customer. Employee number 3 will serve the complimentary drinks or welcome drinks. Employee number 4 maybe will ask for some additional services. Like this, if you divide or distribute the works properly, now what is the advantage now? Once a customer came, employee number 1 immediately go and welcome the customer. Once employee 1 welcomed customer number 1, he is free now. At the same time, if second customer comes, then employee number 1, which is free, he can go to customer number 2 as well. Similarly, after welcoming, your employee number 2 will serve the menu card to the customer 1. And once it served the menu card to the customer number 1, he is also free now. So he can go to customer number 2 immediately after that. You understood the situation? So the first situation is a system without pipelining. Means there is no pipelining, all are busy solving one particular task only. Once the task is done, they are going for the task number 2. You understood that? And situation number 2, where you have distributed the works to all the employees properly, is called a pipelining system. Hope you understood that. Similarly, in our computer system also, whenever we talk about pipelining, what do we do basically? Whenever we execute any program, we divide the task into 5 different stages. Fine. What are the stages? Fetching, decoding, computing, memory access, and write. Once you are executing some program, once you are executing some instruction, so these are the 5 different tasks we perform: instruction fetching, decoding, computing, memory access, and write operation. So without pipelining, what will be happening is your processor will be busy solving one particular instruction. Once instruction number 1 is executed, then it will go for instruction number 2, then it will go for instruction number 3, 4, and so on. And it's a time consuming process. But in pipelining, where what we can do is we can divide the task to some particular hardware. See, whenever we fetch the instructions, all the hardwares are not involved in instruction fetching. Some particular hardwares are responsible in fetching. Similarly, for decoding also, I don't need all the hardwares in my CPU. Some particular hardwares I need. For computing, memory access, and write also. So what we will do in pipelining is we'll divide our hardwares into some groups. Group number 1 will be fetching the instruction. Group number 2 will be decoding the instruction. Group number 3 will compute the instruction. Group number 4 will do the memory access, and group number 5 will do the writing operation. If we do so, parallelly we can execute multiple instructions now. See, instruction number 1, this is clock cycle. In first clock cycle, what I can do, I can fetch the instruction from instruction number 1. Fine, I can start this instruction and I can fetch this instruction. In clock pulse 2, what I will do with the first instruction, fetching is done, I will go for decoding. Of course, this flow of execution will be very important. You cannot mix, after fetching you cannot directly jump for memory access and all. So in clock pulse 2, what I can do now, in clock pulse 1 fetching is done, so the group of hardwares which are responsible for fetching the instructions are free now. So in clock pulse 2 they can fetch some other instructions as well. Fine. In clock pulse 3 they can again fetch some other instructions as well, because they are free now. They have only one task to do, fetching. Once this is done for this particular instruction, they are free to do for other instructions as well. So in clock pulse 1, fetching of first instruction. In clock pulse 2, decoding of the first instruction, and at the same time fetching of the second instruction is also possible. In clock pulse 3, computing of the first instruction, at the same time decoding of the second instruction and fetching for the third instruction is also possible. I hope you understood this concept, how pipeline works. Fine. So this is how your pipeline works in your system. Now, this pipeline block diagram, if you draw a block diagram of pipeline, this is how it looks like. See what we have? Initially we have instruction fetch, then immediately after that we have a buffer. Obviously we need buffer, otherwise there may be some collision. Through buffer only, the whatever instruction you have fetched, it will be forwarded to the instruction decoding fetch. From decoding also, whatever you are decoding, it will be going through a buffer, and from this buffer it will be forwarded to the computing stage. From computing stage it will go through some buffer again, and from the buffer it will be forwarded to the memory access, and from memory access again it will be going for some buffer. From the buffer only it will go for the writing operation, which will be done in some registers. Fine. Now this diagram looks like fine whenever I explain, but there is a confusion that after buffer B1 I should go for instruction decoding. That is fine, I have a way to go, but why this shortcut way to go to B2 directly? It should be like this, right? From B1 it will go there, then it will go to instruction decode, then it will come here, it will come for the computing. But if you see here, I have a direct shortcut bridge also from B1 to B2, B2 to B3, B2 to B4. Why this shortcut bridge is all about? Don't be confused. In some program, some special cases, after instruction fetching itself, you know what is the instruction all about. No need to go for decoding for some special instructions. If so, then we can directly jump for the next stage. You understood that? That's why we have a shortcut bridge also. Typically, we won't go for this shortcut bridge. Typically, we'll follow the flow of the execution. After instruction fetch, we'll go for the decoding. But for some special cases where after instruction fetching only I know what is the instruction all about, no need to go for decoding, I can directly jump for computing. That's why one shortcut bridge is there everywhere. For some special cases, if some cases are like that. Understood that? So this is all about your pipelining concept and the basic block diagram. Now this concept looks like very easy, very simple, and very interesting, but there are some issues as well. What are the issues with our pipelining? We'll discuss now. See, whenever there are some issues with pipelining, we won't say it directly as issues, but we have some standard terms for that. We call it as hazards. We don't call it as pipelining issues typically, we call it as pipelining hazards. We have three different hazards. This is very important to know. First one is called data hazard. Second one is called memory delays or memory hazards. Third one is called instructions hazards or memory branch instruction. Now what is this all hazards about? I will discuss in the upcoming slides. First of all, we will discuss about data hazards. What is data hazards? So before I discuss about data hazards, just imagine about this program where I have two instructions. This program contains two instructions. Fine. What is my first instruction? Add R2, R3 hash symbol 100. What does it mean? This instruction means R2 equals to R3 plus 100. Very simple. Fine. What is the next instruction? Subtract R9, R2 hash symbol 30. What does it mean? This means R9 equals to R2 minus 30. Now when you execute this program, obviously the first instruction will be executed first, then second. Now using pipelining, we know once I have fetched the first instruction, in the second clock pulse I can start fetching the second instruction as well. Fine. Once I decode the first instruction, immediately I can decode the second instruction as well. But there is an issue with this program. What is that issue? See here the first instruction. In first instruction, what I am doing, I am adding something to R3. Here I am doing R2 equals to R3 plus 100. Means there will be some new values to R2. Whatever R2 you have now, you will get some updated values after adding R3 and 100. This will be copied to R2, right? So until and unless you get the updated value of R2, how can you go for the decoding of here in this instruction? You understood that? Because these two instructions are linked. This second instruction will be waiting for the updated value of R2. Should wait, otherwise it will get some old value. It will execute some old value. You understood that? So your instruction number 2 depends on instruction number 1 here. Until and unless your instruction number 1 get the updated value of R2, I cannot perform anything with this R2 here. Otherwise it will be mismatched. So whenever this kind of issues or hazards occurs, we call it as data hazards. Because this hazard or this issue is occurring because of some data. What is that data? The value of R2. I hope you understood that. So this is how it will look like now in traditional pipelining. In first clock cycle, fetching of the first instruction is done fine. In the second clock pulse, decoding of the first instruction is done fine. And in the second clock pulse, same times parallelly I can fetch the first instruction. Fine, no issue. In the third clock pulse, I am computing the first instruction, and at the same time I cannot decode the second instruction because I am waiting for the updated value of R2. So when I can decode it, or when I will finish my decoding, after finishing all these 5 stages of instruction number 1, then only I can finish my decoding, then I can go for computing. Until and unless I get the updated value, I cannot go for the computing. Decoding is fine. I will be in decoding only. I will keep waiting for the updated value. Once I get it, I can go for the computing. You understood that? So to get the computing stage, I have to wait this much time. So now this pipelining is not working properly, right? That's why you call it as hazards, pipelining hazards. And this kind of hazard is data hazards. Now if I tell you, is there any solution for this? Can you propose any solution for this issue? Because this is a big issue, right? Forget about this small program. Your instruction may contain very big information and you have to wait for the whole day to get the updated value. So it's a big issue. So is there any other way to solve these issues? Yes, we have one alternate solution for this. What is the alternate solution? See, what are the stages I have? Fetching, decoding, computing, memory and write. In the previous case, after writing, I have gone for the computing stage for the second instruction. Instead of that, what we can do, if we can do if we can make a bridge so that after computing the first instruction, computing means what? You have done with the calculation. Why we are waiting here in second instruction? Because I need the updated value of R2. Because I need the computed value of R2. Fine. So instead of waiting till write operation, if I can make a shortcut bridge, once you have completed the computing stage, means you have already updated the R2, but you have not written it to the register, but updated value you have now. In computing, you have already computed whatever computation you have. Just you have not written it or updated it to the register. So here, from here, if you can make a shortcut bridge that once you have computed the value, just forward the value to the second instruction. You understood that? Instead of waiting till write, you have computed it, just forward this value to your second instruction so that it can execute the program. Fine. If we can make a shortcut bridge like that, then our problem will be solved. Fine. So this is how we can solve these issues. This is how we can solve the data hazard issues. Fine. Now we'll go for the second type of hazard. The second type of hazard is called memory hazards or memory delays. What does it mean? It means, see, after fetching, decoding and computing, you have a stage called memory access. Means you are searching some data from your main memory or from your cache memory. Sometimes what may happen is, you want to access something from your memory. Initially you will go for the cache memory. If it is available in the cache, then it will be so faster, right? Immediately you will get the data and you can go for the next step. But assume that the data is not present in your cache memory, then what you will do? In that situation, you will go for the main memory. You will ask the data to the main memory. Imagine that it's not available in your main memory also. Then what will be happening? You have to go for virtual memory. Fine. So if you go for virtual memory, you have to search the data, you have to transfer the data to your main memory, from main memory to cache, from cache to execution stage. So sometimes if the data is not available to access easily, it may take more than one clock cycle to complete this memory access. You understood the concept? So if so, then if you are waiting in the memory access stage for the first instruction, so you have to wait that much time for the second instruction as well, if it is interlinked, if they are connected to each other. Fine. So this is how some memory hazards occurs when the data is not easily accessible from the memory. It may be from the cache or main memory or from the virtual memory. It may take more than one clock cycle. This is obvious. You cannot expect always to get the data from cache immediately. So if it is taking more than one clock cycle to get the data from main memory, then it affects the next instruction also, if they are linked or interconnected or dependent to each other. You understood that? Now, is there any shortcut way to overcome from this issue? The answer is no. Unfortunately, we don't have anything to overcome from this issue, because this is related to main memory, or this is related to memory access. If you are not getting the data, you cannot do any shortcut bridge or anything. You need the data. For data hazard, we had a shortcut connection or shortcut bridge option. But for memory access or memory hazard, we don't have any solution for that. We have to wait, because we need the data, whether it is there in cache, main memory or secondary storage or virtual memory, wherever. I need to wait that much time. Fine. So this issue is called memory hazards or memory delays. So we have to wait for this memory access. I hope you understood this concept also. Then we have the third concept. I hope this concept is clear for you, memory hazard, called instruction hazards. Now what is instruction hazards? Instruction hazards means, in instruction hazards we have two types of instruction hazards. One is called conditional branching and one is called unconditional branching. So in unconditional branching, what happens is, we don't execute the instructions every time one after another. Sometimes what we have to do is, because of some branch instruction, we have to skip some instructions and we have to move to some other instructions. Fine. What is, suppose I am executing instruction number 1. So fetching is done. Then after fetching, next I am going for decoding, next computing. Then maybe I got some branch instruction that go to instruction number ik. Fine. This is the instruction you have to execute here. You got some branch instruction. The branch is go to ik, execute this first, then come back. So fetching, decoding, and computing. After computing, or whenever you are in computing, what you got? A branch statement. What is that branch statement? Go to ik. Means you have to come here in ik. You have to finish this execution first. Once everything is done, then after that you can go for the next stage of instruction number 1. So unnecessarily you have to wait for some clock cycles, because you have to jump to a particular instruction. You have to finish it, then only you can come back to the present state. You understood that? So this is called branching or instruction hazards, where you have some branching. Branching may be unconditional or conditional. This is unconditional, right? Without anything, I am telling you to go to ik. Now if I talk about conditional branching, means there will be some conditions. If this condition is satisfying, then only go for that particular branch or statement or instruction. I hope you understood that. In conditional branching also same thing happens. Whenever some condition satisfies, you have to go for that particular instruction, you have to execute it, then only you can come back for the present execution step. So that's all about pipelining in short. So I hope the basic concept of pipelining is clear for you. So in the next video we'll discuss about